Okay, in the last lesson, we looked at graphs of a polynomial, and specifically we looked at end behavior. So originally when we looked at graphs, we were looking at where the graph was increasing or decreasing as we went left to right. The difference with end behavior is that we're looking at the graph as if we're standing at the center. So again, increasing, decreasing, think of it as you're walking across the graph, going from left to right, and you're saying, what's happening as we go across the graph? Is it increasing or decreasing? Okay. Whereas the difference with end behavior is you're standing in the very middle of the graph and you're looking to the right and you're saying, what's happening to these y values? Are they going up or are they going down? And then same thing, you're looking to the left and then you're saying, are they going up or are they going down? Okay. So one thing that I forgot to mention with end behavior is that we can say that both sides rise, or we can say that one side rises on the left and falls on the right, or vice versa. We can also say that both sides fall. But I didn't talk about how we might write those symbols. So I just want to put that in there so that it's clear. Okay. So first, let's go back to end behavior. So you can see the ends of the notes from the last lecture. So end behavior, if we have odd degree, and a positive leading coefficient. Okay. Remember, I'm abbreviating leading coefficient as LC. What this means is, and you can see this above, that if it's odd degree and a positive leading coefficient, it means that each side does different things, and then it also means that it's going to rise on the right. So we're rising on the right, and we're falling on the left. Okay, here's the thing though, this is not a nice way of writing it. It's wordy, and in math we do usually prefer symbols. So when we talk about going right and left, we're talking about the x values. So going right and left means x values. Whereas when we're saying rising or falling, we're talking about the y values. And if you remember, our y values are the same thing as f of x. So if we're saying that we rise on the right, we're saying, well, as x approaches infinity, okay, so our x is going to positive infinity, our y is going up. So f of x is also approaching infinity. So increasing or rising is approaching infinity. Decreasing or falling is approaching negative infinity. Okay, so if we're talking about the left, as x approaches negative infinity, because we're going left, in this case f of x is approaching negative infinity. So the right is the x approaches infinity, and the left is the x approaches negative infinity, whereas the rise says f of x approaches infinity, and the fall says f of x approaches negative infinity. Okay, so rising means our y values go to infinity, falling means our y values go to negative infinity. Going to the right on a graph means that our x is going to infinity, and going to the left on a graph means that our x is going to negative infinity. Think about our axes. So if we go here, we can see the axes. When we go to the right, our x values, it's our x values that are approaching infinity, and as we go to the left, our x values are approaching negative infinity. Whereas with rising and falling, we're talking about the y values going up or the y values going down. Okay, so that's an odd degree and a positive leading coefficient. So we could have an even degree and a positive leading coefficient. And for an even degree and a positive leading coefficient, we know that both sides rise. So here again, we're talking about as x approaches infinity. And since it rises as x approaches infinity, we say f of x approaches infinity. And here, as x approaches negative infinity, meaning as we go to the left, f of x also approaches infinity. So that's even degree and positive leading coefficient. Okay, let's talk about odd degree. And a negative leading coefficient. So odd degree says that they're both doing different things. A negative leading coefficient means that it's going to fall on the right, but rise on the left. So remember, it rises on the negative side here, and the left is our negative side. So if it falls on the right, so the right says as x approaches infinity, it's going to fall. So when we fall, our f of x, our y values, go to negative infinity. So negative infinity means we're going down. And here now on the left, so as x approaches negative infinity, our f of x approaches infinity because on the left we rise. And then finally, we can say if we have an odd degree, an even degree, and a negative leading coefficient. The even says they're doing the same thing. The negative leading coefficient says that they both fall. So as x approaches infinity, as we go to the right, f of x approaches negative infinity, we fall. And as x approaches negative infinity, we go to the left. F of x also approaches negative infinity. We fall. So we can recreate this chart that we have up here. We can recreate it, only this time, when we recreate it, we're going to use this terminology. Okay, so let's do that so that you have it. I'm just going to move this up here so that you can see it. didn't seem to be coming up. So again, we have our leading coefficient, and we talk about it being positive or negative, and then we have our degree, and we talk about our degree as even or odd. So if it's an even degree and a positive leading coefficient, then we know that both sides are doing the same thing. As we go to the right, we rise. As we go to the left, we also rise. Okay, an even degree, if it's negative, they're both doing the same thing, but it's the opposite. As we go to the left, or I'm sorry, to the right, to positive infinity, we fall, so we go to negative infinity. And as we go to the left, we also fall, so we go to negative infinity. Okay. For an odd degree, we know that each side is doing different things. So notice all of them, you see x approaches infinity and x approaches negative infinity. That's because we're always talking about left and right, okay? Whereas the f of x could be doing the same thing or different things. So when we have an even degree, they're both doing the same thing. In this case, they're both going to positive infinity. In this case, they're both going to negative infinity. When we look at odd degree, you're still going to see x approaches infinity and x approaches negative infinity, because we're talking about what happens on the left versus what happens on the right. But these f of x's, one is going to approach infinity, one is going to approach negative infinity. So they're doing different things. So if it's odd, the leading coefficient is positive, which means it's going to rise on the right. So f of x is going to approach it, f of x is going to approach it positive infinity. And as we go to the left, we're going to fall. So f of x is going to approach negative infinity. If it's odd and the leading coefficient is negative, then it's the opposite. As we go to the right, we fall. So f of x approaches negative infinity. And as we go to the left, we rise. So f of x is going to approach positive infinity. Okay, so that's the end of end behavior. I just wanted to make sure that we cover that. So now let's talk about actually how we can predict what the graph of a polynomial looks like. And I want to be clear here. It's a prediction. It's a sketch. It's not perfect. Okay, the only way to get a perfect graph is to plug in points, and if we know calculus, we can get a better, even more accurate prediction of the graph. So there are a few things that we're going to look at. We're going to look at the zeros or the roots, okay? So we're going to look at, actually, we look at the end behavior. We look at the zeros or the roots. Remember, these are interchangeable. And we look at the multiplicities of those roots, which I will explain. We did not talk about this yet. So one thing that we should know, we know that a polynomial with degree n has at most n zeros. Okay. And we actually know that it has at most n minus 1 turning points. Okay, so a polynomial with degree 5 can turn around a maximum of 4 times. Remember, a turning point is where we go from increasing to decreasing. Or decreasing to increasing. This is what we mean by turning point. Okay. So what this helps us do is it helps us figure out where our turning points are. It also helps us figure out what is happening at the roots. Okay, so let's look at the roots first. We know that if x minus a is a factor, x equals a is a root. So for example, let's take the polynomial in factored form x minus 2, x plus 1, x minus 3. Okay, so this is a polynomial in factored form. And this is going to be important to recognize when a polynomial is in standard form, like 3x to the 5th plus 2x to the 4th minus 7, and when it's in factored form. So we have factored form, you can see there are parentheses. In standard form, you do not have parentheses. So we're saying x minus 2 is a factor. So x equals 2 is a root. This is nothing new because we did this with quadratics. Then we're saying x plus 1 is a factor. So x equals negative 1 is a root here. And x minus 3 is a factor. So x equals 3 is a root. Okay. In order to figure out the multiplicity of a root, what we're going to look at is whether or not any of these factors have exponents. So if there is an exponent here, the multiplicity is equal to the exponent. Okay, so the multiplicity of a root is the exponent of the factor. So, for example, all these roots, x equals 2, x equals -1, x equals 3, have a multiplicity of 1. Okay, that's because the exponent here is equal to 1. Okay, remember, if there is no exponent, the exponent is 1. So let's take another example. Let's say that we had f of x equals x plus 6, and this time we're going to raise this to the third power, x minus 4 squared, and x plus 5. And that one we won't raise to a power, which means that it's raised to the power of 1. Okay, so in this case, the roots are x equals -6, x equals +4, and x equals -5. Okay, we set each factor equal to 0. And then solve for x. That's how we can find the root. Again, this should not be anything new to you. Now we can find the multiplicity of each root. So if we look at x equals -6, okay, for our x equals -6, if we look at the exponent here, it's 3. So 3 is the multiplicity. At x equals 4, if we look at the exponent here, we can see that it's 2. So 2 is the multiplicity. And at x equals -5, we can see that there is no exponent, so the multiplicity is just 1. Okay. If we do the same thing again, let's take another. Function. I'm going to call it g of x this time. So if we say g of x equals x minus 3 to the 5th, x plus 1 to the 8th, x minus 2 to the 4th, x plus 5, and x plus 7 squared. Okay. Then we could find each of the roots. So we'll make a little table here. We'll have the roots, and then we'll have the multiplicity. So our roots here, from x minus 3, we have the root x equals 3. From x plus 1, we have the root x equals -1. From x minus 2, we have the root x equals 2. From x plus 5, we have the root x equals -5. And finally, from x plus 7, we have the root x equals -7. And remember that the roots are also the x-intercepts. Okay, it's where we cross the x-axis, which becomes important because it tells us something about the graph. Okay, if we look at the multiplicities of each of these, that's actually going to tell us something about the graph too. The multiplicity of x equals 3 is 5. So this is what's giving us the multiplicity. Okay, right here. The 5. Then we have the 8 for the x equals -1. The 4 for the x equals 2. Here there is nothing here, but we know that it's a 1. And then for the x equals -7, we have a 2. So we're getting the multiplicities from there. Okay, so we have x equals -1, as we said. We know that the multiplicity is 8. X equals 2, we know that the multiplicity is 4. Again, we're just looking at those exponents. For x plus 5, for x equals -5, the multiplicity is 1. And for x equals -7, the multiplicity is 2. Okay, here is what the multiplicity tells us about the graph. It tells us what's happening as we cross the x-axis. So when we cross the x-axis, one of two things could happen. Either it's going to pass through the x-axis, or it's going to bounce off of the x-axis. Okay, so if we pass through the x-axis, the multiplicity is odd. And there are two ways that we could pass through the x-axis. Here's your x-axis. You can either pass from left to right, or from positive y value to negative y value, or from negative to positive. So in other words, you're either passing like this, where you are above and then you're going below, or you can pass through like this. So you're below and then you're going above. So it's two different ways to pass through the x-axis. If you have an even multiplicity, what that means is that you're bouncing. Think of the x-axis as a wall. So again, here's your x-axis. And either you're bouncing above the wall or you're bouncing below the wall. That's going to depend on where you are in the graph. So this would be a bouncing off. If you're above it, you hit the wall and then you bounce off. So that's one way to bounce off of the x-axis. Or you might be below the wall when you start. So if you're below, then you're bouncing like this. Okay, where that is your root right there. Okay. So again, you hit the wall, you bounce off of it. Whereas for an odd multiplicity, you can go right through it. So if we look at the multiplicities up here, so up here, This has a multiplicity of 3. So we're going to pass through the x-axis. Then we have a multiplicity of 2. So we bounce off of the x-axis. And then we have a multiplicity of 1. So we're going to pass through the x-axis. If we go to g of x, then when we have a multiplicity of 5, we pass. When we have a multiplicity of 8, we bounce. Multiplicity of 4, we bounce. Multiplicity of 1, we pass. And a multiplicity of 2 says we bounce. This has nothing to do with the root. It's completely independent of the root. So to determine if we pass or bounce, we only look at the root, not the we only look at the multiplicity, not the root. So if you look up here, you can see that x equals -7. It doesn't matter that 7 is odd. What we care about is the 2. We care about the multiplicities. The multiplicities are telling us whether we bounce or pass. Only those numbers, okay? These roots are completely independent of that. Okay, so now we have all the information we need in order to sketch the graph of a polynomial. So one last thing. When we look at end behavior, right, we have to determine, are we rising on the left? Are we rising on the right? What's going on? And we look at the degree of the polynomial and the leading coefficient. So when you're trying to graph a polynomial, you're putting it into factored form because you want to know what the multiplicities of the roots are, and you have to find the roots. So all of the polynomials that we're working with are going to be in factored form when you're asked to sketch a graph of those polynomials. Okay, so what does this mean? Let's take f of x, okay? Imagine if you multiplied out f of x. Now we know that the degree of a polynomial in standard form is the highest power in that polynomial. If we took f of x and we spent the time to multiply it out, we would have an x cubed coming from here. We would have an x squared coming from here. And we would have an x coming from here. And when we multiplied x cubed times x squared times x, you would wind up with an x to the 6. That's because you add the exponents. 3 and 2 and 1 is 6. Okay? So if you were to multiply this out and put it in standard form, the highest value of x is actually the sum of these multiplicities. The same thing would be true here. X minus 3 to the 5th would give us an x to the 5th. X plus 1 to the 8th would give us an x to the 8th. X minus 2 to the 4th would give us an x to the 4th, and so forth. So if we want to find in standard form what the degree is, we can take the sum of the multiplicities, okay? So the degree of a polynomial and this is a common mistake that people make, so make sure that you really think about this as you graph. The degree of a polynomial in standard form is the highest power of x. the degree of a polynomial in factored form. So again, this is factored form that you've been seeing because there are parentheses. Is the sum of the exponents, or the sum of the multiplicities. Here's what that means. Let's just use f of x and g of x. The degree is equal to 3 plus 2 plus 1, or 7. The degree here is equal to 5 plus 8 plus 4 plus 1 plus 2. Which in this case is 20. Okay, so these have even degrees, So the degree here is 7, not 3, okay? The degree is 7, which means that it has an odd degree. Here the degree is 20, okay? Which means that it has an even degree. It just so happens that here the highest exponent is 3 and the degree is 7. Okay, so the highest exponent has nothing to do with the degree in this case because they're in factored form. Okay, the leading coefficient is going to be the number that you see in front. So here we don't see any number, so the leading coefficient is 1. And here the leading coefficient is also 1. Okay, so the leading coefficient, I'll put that over here. Is just going to be whatever number is in front of all the factors. And again, we're going to do examples. Okay, so let's actually start graphing some polynomials. So we graph using multiplicities, roots. The Y-intercept can be helpful here, so I'm going to include it, and an end behavior. Okay, so we're not going to graph these. I'm going to give you a new function. So let's let f of x equal 3 times x minus 1 squared times x plus 2 times x plus 1 to the 4th. Okay. So let's start by identifying the end behavior. Okay. So if you remember, in order to determine the end behavior, we need to know the degree. So in order to find the degree, we add the exponents. So 2 plus 1 plus 4 is equal to 7. So the 2 comes from here. The 1 comes from this exponent over here. Again, if there is no exponent, it's a 1. And the 4 comes from here. So 2 plus 1 plus 4 means that we have a degree of 7. All we care about is whether it's even or odd, and this one is odd. The leading coefficient is just 3. So we look at this number in front to figure out the leading coefficient. Okay, here's our leading coefficient. So all we care about here is whether it's positive or negative, and it's positive. Okay, and here you don't have to worry so much about writing it using f of x and x. You can just say, okay, an odd degree says that we're doing different things on the left and right. The fact that it's positive tells us that it's the right that's rising, so the left is falling. So we can just write that the right rises and the left falls. Okay, and this is the first thing that we're going to use to help us figure out, okay, what is going on in this graph. The next thing that we're going to look at is the roots and multiplicities. So let's just write the roots. We'll do it in a table, just like we did before. And from here, we can also tell whether it passes or bounces off the x-axis. So our roots come from the x minus 1, the x plus 2, and the x plus 1. So our roots are x equals positive 1, because remember, we take this x minus 1 and we set it equal to 0. X equals negative 2. And x equals negative 1. Our multiplicities come from the powers. So the multiplicity of x equals 1 is 2. The multiplicity of x equals negative 2 is 1. There is no power, so it's just 1. And the multiplicity of x plus 1 is 4. So notice that this is x plus 1, but our root is x equals negative 1. This is x plus 2, but our root is x equals negative 2. And this is x minus 1, but our root is positive 1. Okay. And since the multiplicity is even, that tells us that it bounces. Here the multiplicity is odd, so that tells us that it passes. And here the multiplicity is even, so it bounces. And then the last thing that we care about, so I'll highlight this. The things here that we are going to need to know are the x equals 1, so the roots, the x equals negative 2, the x equals negative 1, and then whether or not it bounces at the root or passes at the root. So everything that I'm highlighting are the things that we're going to need in our graph. And then the last thing is the Y-intercept. So the Y-intercept, again, it can just be helpful in telling us what's going on. So our Y-intercept is when when x is equal to 0. So we're going to plug in to f of x, x equals 0. So we have 3 times 0 minus 1 squared times 0 plus 2 times 0 plus 1 to the 4th. Okay. And just be careful here. There's no, you're multiplying. This becomes 3. 0 minus 1 is negative 1 squared. 0 plus 2 is positive 2. And 0 plus 1 is 1 to the 4th. This is an order of operations problem. -1 squared is 1. So you're doing 3 times 1 times 2, and then 1 to the 4th is 1. This is all multiplication. In the past, I've had students, for some reason, add in addition signs. You're multiplying all of this. It's 3 times 1 times 2 times 1. And we get 6. So our y-intercept is 0, 6. Okay, so let's graph this. So this is the last thing that we're going to be looking at. Whoops, I'm sorry. Okay, so everything that's highlighted, we're going to be using in our graph. I'm also going to order it. You look at the end behavior first. So this is the first thing that you look at. Then you can mark off your roots and you can use your multiplicities. And then you do the y-intercept. The order matters. The reason why the order matters is that the end behavior is going to tell you in which direction it bounces. So if you remember, when we talked about bouncing and crossing, we said it could bounce in 2 different ways. Either you're coming from above the x-axis or you're coming from below the x-axis. Here, you're going either from top to bottom or bottom to top. And these arrows really aren't accurate. Because you're going into the x-axis and then coming out of. And then same thing here. You're going into the x-axis and then coming out of. And actually over here, you can be going, we always talk about left to right. So when we travel across a graph left to right, it's going to look like that. Okay. I'm just trying to decide if I should try and use this page. Okay, I'm going to try and use this page. If it's too small, then we'll adjust it. So you're going to draw your axis first. Okay, I'm going to put a note here that you want to mark off the roots on the graph first. So even though you deal with whether it bounces or passes second, the roots you're actually going to mark off first. So here's our x, here's our y. And we have roots at x equals 1, x equals -2, and x equals -1. So we have roots in these 3 places. Here, here, and here. Those are the first things that we're going to do. So this is our -2, our -1, and our 1. Okay. The next thing that we're going to look at is our end behavior. So on the right, we rise, and on the left, we fall. So we can mark that off, and we're going to do it rather loosely because we're not sure yet if we're bouncing or passing at those roots. So we're just going to do it very generally. So on the right, we rise. So we know that coming up from the 1, so comes from the last root. On the right, we rise, and on the left, we fall. Okay, so we mark that off second. The next thing that we do is we look at the multiplicities. So the multiplicities are going to tell us, are we bouncing or passing? So this tells us that at x equals 1, we're bouncing. So we're above over here, so we know that we have to be coming from above in order to bounce. If we were coming from below, then we would be passing through the x-axis. So we know that we have to bounce, okay? At x equals -2, we pass. And because we're coming from underneath, that means that we're going to above. And then finally at x equals -1, we bounce. So we know because we were above after -2, we know that we're going to wind up above at -1. And as we go left to right, we wind up bouncing, okay? Now this is where we really don't know what's going to happen. We don't know our turning points. So we're just going to approximate here. Now we know that the y-intercept is at 0, 6, so we can mark that off next. So here's 6, and we can mark off the y-intercept next, okay? And we know that we're going to pass through that, but what we don't really know is the turning point. We don't know how high up we go. So this is where it's a sketch. So if we finish the sketch, we're going to approximate the turning points. So we're going to go through this 6. We don't know for sure if that's actually the turning point, but we can approximate. And in order to figure out the turning point, essentially what we want to know is we want to know, are we turning before 6 or are we turning way up here somewhere? Okay, if we're turning way up here somewhere on the graph, then what that's going to tell us is that we're actually not going to show the connection. So what we can do is we could sort of just plug in like a -1/2 and get some idea as to how high this is going to be. And this is actually going to be pretty low if we plug in a -1/2. So it's going to be it should be a relatively low turning point because -1/2 minus 1 is a -2.5 squared, which is positive, times a 3. So we're talking about something around 6. Then we're cutting it in half, and then we're cutting it in half again. So it's probably going to be a low turning point. So we can just draw it like that. Again, it's not perfect. We're just approximating. Okay, and that would be the finish of the graph. And if we go into Desmos and we type this in, well, I actually typed it in already over here. So we're going to look at this graph and we can see. So when it went through 6, that wasn't the actual turning point at 6. Okay, but again, this is why we call it a sketch. Okay, we know that between -1 and 1, we know that it has to turn around. We know that it had to turn around between -2 and -1. Okay, so it turned around. We passed through at -1. We bounced. Sorry, at -2 we passed. At -1 we bounced. And at 1 we bounced. And we go off to positive infinity and negative infinity. So notice in the little sketch that we drew, we have arrows at the end. Okay. Let's do another example. So let's take g of x is equal to negative x plus 2 squared x minus 1 to the 5th and x plus 3. So we're going to be looking at 3 things. Again, we're going to be looking at the end behavior, the roots and multiplicities, and the y-intercept. So let's start with the end behavior. So for end behavior, the first thing that we have to do is figure out the degree. The degree we get by adding the exponents because it's in factored form. So 2 plus 5 plus 1 gives us 8. And what we care about is the fact that this has an even degree. The leading coefficient, there is no leading coefficient here. There's no number here, but there is a negative. So the leading coefficient is -1. And again, all we care about is whether this is positive or negative, and it's negative. So an even degree says both things are doing the same thing. The negative says that they're falling. So the end behavior says both sides fall. The next thing that we want to do is the roots and their multiplicities. So we can just create a chart here. So the root, the multiplicity, and then whether it bounces or passes. So our first root is x equals -2. So we're getting that from the factors. The factor is x plus 2. Remember that if we're solving for the roots, we're setting each factor equal to 0. So if the factor is x plus 2, then the root is x -2. The next one, our root is 1. And finally, our root is -3. To find the multiplicities, we look at the exponents. So our exponent here is 2. Our exponent for the x minus 1 is 5. So the multiplicity is 5. And our exponent for x plus 3 is 1. Now this will tell us whether it bounces or passes. So the multiplicity is even, which means it bounces. The multiplicity is odd, which means that it passes. And this multiplicity is also odd, so we know it passes. Sorry. Okay, and then the last thing is the Y-intercept. So Y-intercept is when we have f of 0. So we have -0 plus 2 squared, 0 minus 1 to the 5th, 0 plus 3, which gives us -2 squared, -1 to the 5th, and 3. Only the 2 is being squared, not the -2. So -4, -1 to the 5th, the negative is inside the parentheses here. So the negative is being raised to the 5th. -1 to the 5th is -1 times 3. So -4 times -1 is +4 times 3 is 12. Again, we're multiplying. So our Y-intercept is 0, 12. So the things that we care about. We care about the fact that both sides fall. We care about whether or not it bounces or passes. We care about the roots. So x equals -2, x equals 1, and x equals -3. And we care about the Y-intercept. So if we graph this, okay, we know that we're going to have 0, 12 in there, so it's going to have to go up high. So I'm going to spread these roots apart a little bit. Here's our x. Here's our y. So we mark off the roots first, okay? So x equals -2. So these are our roots. We know that we're going through the x-axis here. Now we have to figure out the end behavior, okay? Again, the end behavior has to come first because otherwise you won't know in which direction you're bouncing or passing. So let's mark off the end behavior. We could do that in green. Now we know that we're falling on both sides. So on this side we're falling. Again, we're doing this lightly because we don't know for sure yet if we're going to be passing or bouncing at these points. Now we could do the passing and bouncing. So at x equals -2, so I would do the ends first, okay? Don't do the middle roots, do the ends. So at x equals -3, it passes. So we know that we're going in this direction. At x equals 1, we're also passing. So we know that we're going in this direction. And then at x equals -2, which is the one in the middle, we're bouncing. And you can see that before we were above, so we're coming from above. So it's looking like this. Okay. It should be a little bit more centered though. So it looks like that. Now it's just a matter of doing the last connections. So the y-intercept is going to help us here. Okay, we know that the y-intercept is at 0, 12. So let's mark off up to 12. We'll do this part in blue. So here's 12. And we know that we're going through the graph there. So if we connect everything, again, we don't know for sure that this is the turning point. Okay, it's approximate. And we do know that we turn somewhere between 3 and -2. So again, I would just use your calculator. Plug in -2.5. So if we plug in -2.5, so we're choosing -2.5 because it's a value between the roots -3 and -2. And this is just to see where it turns. So if we plug in -2.5, -2.5 minus 1 is actually very large. So if we do -2.5 minus 1, we get -3.1 to the 5th. It's actually a really large number. So we get a large number . So we just indicate the turning point. With a dashed line. In other words, it goes off the graph. So we're just going to go up here. We're going to go up here. And I'm just going to put like a dashed piece there just so that you can see that it goes up off the graph. And if we look at that in Desmos, that's this one here. And you can see it goes way up off the graph. And even the -12, it wasn't completely accurate because we turned around. We went through the graph there, but we actually went even higher. So the turning point was higher up. So again, this is a sketch. It's not perfect. Okay, you can see that it passes at -3. It bounces at 2. And because the exponent is high here, right, the degree here is 8. So it's a high exponent. You can see that it flattens out near this root. Okay, and so again, this is why it's a sketch. It's never going to be a perfect graph. It's just going to give you an idea as to what happens. And it allows you to go backwards too. So if we look at this graph, we can see that both sides are falling. So we know that we're going to have an even degree and a negative leading coefficient. We can also see where the roots are. So we can see that we have a root at -3, -2, and 1. And we know the multiplicities. We don't know the exact multiplicities, but we know whether they're even or odd. So this passes, so we know that this has a multiplicity that's odd. This bounces, so we know that it has a multiplicity that's even. And this passes, so we know that it has a multiplicity that's odd. Whereas with the other one, again, now that you've been away from it for a couple of minutes, you can see, right, this, we know that the leading coefficient is we know that the degree is negative because each side, the end behavior is different. We know that the leading coefficient is positive because it rises on the right but falls on the left. We know that the roots are at -2, -1, and 1 because that's where it crosses the x-axis. And we know that the multiplicity at -2, even though we don't know what it is, we know it's odd. The multiplicity at 1 is even. And the multiplicity at -1 is even, and the multiplicity at +1 is even. So we don't know the exact equation, but we do know something about this graph. Okay, let's do one last one, just so to make sure that you got the hang of it. So we'll call this one h of x. We'll make it -4 x plus 1 to the third, x minus 1 squared, and x minus 2 squared. So again, we'll figure out the end behavior first. Notice we always approach this in the same way. The order in which you figure out the end behavior, the roots, and the multiplicities doesn't really matter, but the order in which you graph them does. So here, the degree is 3 plus 2 plus 2, so it's 7, meaning it's odd. So we're adding, okay? We add when it's in factored form. The leading coefficient here, so our number in front is a -4. That's our leading coefficient. And all we care about is the fact that it's negative. Again, since we're just using this for our own reference, when we draw the graph, we don't have to worry about the as x approaches infinity or anything. But what this does tell us is that it's odd. So the behavior on the left and the right is different. And the leading coefficient is negative, which tells us it rises on the left. It rises on the negative side. So it rises on the left. And it falls. Sorry about that. It falls on the right. Okay, and just so that you have it, what this is saying is as x approaches negative infinity, f of x approaches infinity. So the x approaches negative infinity means it's going to the left. F of x approaches infinity says it rises. As x approaches positive infinity, that's going right. F of x goes to negative infinity, we're falling. That's just to review. Okay, now we have the roots and the multiplicities. So we have our roots, our multiplicity, and then whether it passes or bounces. So our roots are x equals -1, x equals +1, and x equals +2. So again, that comes from up here. X plus 1 equals 0 gives us x equals -1. X minus 1 equals 0 gives us x equals +1. And x minus 2 equals 0 gives us x equals +2. The multiplicity for -1 is 3 because the exponent over here is 3. The multiplicity for x equals 1 is 2. And the multiplicity for x minus 1 is 2. An odd multiplicity says that it passes. An even multiplicity says that it bounces. And finally, we can look at the y-intercept. So that's f of 0. Y-intercept is when x equals 0. So we have -4 times 0 plus 1 cubed times 0 minus 1 squared times 0 minus 2 squared. So x equals -4 times 1 cubed times -1 squared times -2 squared. This gives us -4 times 1 times 1, because the negative is getting squared, times 4. Again, the negative is getting squared. So we get -16. So our y-intercept is 0, -16. This will help us also figure out if we made any sort of mistake in our graph, because if it doesn't make any sense, then we know we did something wrong. So for example, in the last graph we did, okay, we would have known something didn't make sense if we put down -12, because our graph, it wouldn't be possible for it to go through a -12, okay, because we're above the x-axis at this point. And even in the one before that, the graph that we did before that, our y-intercept was at 6. If we had written -6 or we had gotten a negative number, that wouldn't have made sense, because our graph has to be above the x-axis given the multiplicities. Okay, so if we go back to this one, we're ready to graph. We know that we are going to have the 0, -16. We have the passing and bouncing. Then we have each of our roots. These are the things that we care about when we graph. And then the fact that it rises on the left and falls on the right. So I'm drawing a nice big y-axis because I know that we have to go to -16. So the first thing that we're going to mark off are the roots. So we know that we have a root at -1, we have a root at 1, and we have a root at 2. And we're going to mark those off right now. -1, 1, and 2. So that came first. Then we're going to do our end behavior. So it rises on the left and falls on the right. So here's our rising, here's our falling. Okay. Then we're going to do the passing and the bouncing at each root. So again, start with the roots that are on the end at the -1. So at -1 it passes. So if it passes, we know that it goes through the x-axis. At 1, at 2, it bounces, and at 1, it bounces. So at 1, we're coming from underneath. It's bouncing, so we stay underneath. We hit that x-axis and we bounce off of it. And then at 2, it also bounces. So we're hitting that wall and we're coming around. Okay. Okay. And our final step is just to connect everything. This is the key. Once you get to this point, your connection is never going to be that accurate. So if you get to this point, you're in really good shape. So on a test or something, you'll get pretty much full credit for this. Okay. You could just show that this goes off the x-axis. Sorry, off the graph, just with the dashed line, but we have the room here, so we may as well show it. And again, we don't know for sure that it turns over there, so it's just an approximation. And if we want to know what's happening between 1 and 2, we could just approximate. Okay, if we were to put in 1.5, for example, 1.5 plus 1 gives us, you're just kind of plugging it in and approximating. We know that we're going to be multiplying something by -4. Just plug in with your calculator and see, does it go off the axis or not? And this gives us a 1.5 plus 1 gives us a 2.5. You raise it to the third power and multiply by -4, you get a pretty big number. So we're just going to show it going off the graph, meaning we go to the bottom of our graph, and then you could just leave it like that, or you could put, as a dashed line, just a little piece like that, just to show that there actually is it will turn somewhere between there. And if we go into Desmos and we graph this, so this one I don't have in here, we have -4 times x plus 1 to the third power times x minus 1 squared, and then times x minus 2 squared. And you can see here, okay? And actually, I did it incorrectly. I wasn't quite correct. It turns much faster than I thought. But if you plug in 1.5, then you would notice that. So over here, we can see it passes through -1. Okay. It bounces off at 1, and we're underneath the graph. It bounces again at 2, we're underneath the graph. And this was the only thing I misjudged. I misjudged this turning point right here. I thought it was much more negative than it actually was. So, but if you plugged in 1.5, you would have seen that turning point was a lot closer. So in fact, if we go back into those notes there, let me fix that. Okay. And we can erase those lines there. Okay, so it looks more like that. And that's our final graph. And just because it's here, let's take a look at this one because we haven't looked at this one yet. So this is an x cubed and a 3x minus 4. So the root here is x equals 0. Okay, at x cubed, the root is x equals 0. And then we have 3x minus 4, and the root there is x equals 4/3. So if we take 3x minus 4 and we set it equal to 0, our x is at 4/3. So if we look here at this graph, we see a root at x equals 0, and there's another root. This root is at 4/3 here. Okay, the multiplicity at x equals 0 is 3. So we can see here that it bounces. And the multiplicity at 3x minus 4 is 1. Multiplicity at x equals 0 is 3, so it passes. I said it bounces. I meant to say it passes. 3x minus 4, the multiplicity is 1, so that also passes. And then the end behavior, the degree here is 3 plus 1, so we still add the exponents. The degree is 4. The leading coefficient is 1, so we know that both sides rise. Leading coefficient is positive. Degree is even, so both sides are rising. Okay. And if we plugged in x equals 1, you would see that you get something close to -1. Okay. So we can predict different things about our graph. Certainly we can predict the roots. We can figure out whether it's passing or bouncing, and we can see the end behavior. Okay. Okay, so that's it for polynomials. There's nothing else to cover. Our next unit is going to be exponents and logarithms, and you will have a quiz, I would say, on Wednesday. I already posted the review sheets for that quiz. I'm also going to, the next set of lessons, it'll be 1 or 2 lectures, probably about a half hour long. We'll just review all of the different things that we covered in class, and maybe a couple more examples of end behavior and graphing polynomials. And that is it.